Welcome to Built Environments. This is an opportunity for Steve and I to talk candidly about products or conditions and things that we have found that may be of interest to you. So today we're specifically talking about deliquescence, what that is, why it matters, and hopefully understand where our products kind of go in use in the market. So today we want to talk about this product. So Steve, what do you have?
Today I want to talk about this product called LP Flame Block. The reason it's interesting to me, it's magnesium oxide joined to OSB. You have two materials, both of which are very hygroscopic, means they absorb water from the atmosphere, potentially causing some moisture problems to the OSB beneath.
So we're talking about water vapor.
We're talking about water vapor. Okay. And so there's been a lot of talk about NGO and how hygric it is. And it's interesting to me that there's folks out there joining a very hygric material onto a water absorptive material that's not just water absorptive, but it's also vulnerable to degradation, swelling, and so forth.
So that was a lot of water absorptive. Really, what we're talking about is the ability of the material of both the coating of magnesium oxide as well as the substrate of OSB that's absorbing significant amounts of water vapor from the air that can cause other concerns and issues that we have on a construction site.
Exactly right. So what happens if you were to put this into a high humid environment?
So what's high humid?
90% would be considered high humid.
So 90% RH, or relative humidity. So you only need to go to about 90% RH before you see this absorptive type material have concerns.
Absolutely. You could actually go lower than 90% depending upon the free salts that are in magnesium chloride. So we're really talking about salts here.
Okay.
Let's say, for example, with magnesium oxychloride, we're talking about magnesium chloride. If we're talking about magnesium oxysulfate, we're talking about magnesium sulfate.
So is this only to magnesium chloride, or is this to all salts, whether it's chloride or sulfate?
All salts.
Okay.
Because any salt, most salts, for example, I should say, have some ability to what we call deliquesce.
So let's define really what is deliquescence.
Well, deliquescence is a simple process, actually. It's the process by which a salt will adsorb moisture from the atmosphere and then dissolve into it, going from a solid state into a liquid state. And there it will exist on the surface of the material as a little bubble, as a droplet of water.
As water droplets, right? So what we're really talking about is the material's ability to go from a solid to a liquid with deliquescence, and it releases those salts in that liquid on the face of that material.
That's right.
And to put words in your mouth a little bit, that can happen at 90% RH in the case of magnesium oxide.
It could even happen at lower than that. The key how a salt deposit starts to form is then that water starts to evaporate off, leaving behind the salts.
Okay, so why is that important? That's the major question that everybody wants to know, especially with magnesium oxide. We've had issues in the past of materials having this crying effect of really weeping, right? And that's really just those deposits, that liquid material showing itself on the face, which is carrying that salt. So why does that matter?
Well, salts in general are going to be very corrosive, some more corrosive than others. And when you have that deposit onto a surface that might be at the interface of a fastener, a screw, or a nail, then you're expressing that salt in a concentrated manner exactly where you don't want it, right at the fastener.
So that salt can do what to materials? Why does it matter?
It will corrode, it will degrade,
Okay.
It will cause it to fail prematurely.
So it can corrode what, like fasteners or studs, for example?
Stud edges, faces, you can corrode the fastener itself, whether it's coated or not. All protected metals are to some degree vulnerable to corrosion.
Okay, so we look at the corrosion scale, and we have different materials that have coatings. We have epoxies, we have dips, we have galvanization processes. Are we talking about all those materials are susceptible?
Yes, some less so than
Right,
others.
and it's to the degree of deliquescence, or those salts that become visible and liquid that come in contact with that steel type material, right?
Exactly right.
Okay, so why this product? Why does it matter? How do we test for it? Like, give me some data.
Yeah, well, I'll use that 90% relative humidity. That's where in the past, when I've looked at this material, I put it 90% or even higher than 90%. And I saw what happened over time, 24 hours, 72 hours, and so forth. What I've learned is that...
what happens?
What happens is that it does deliquesce. In other words, it weeps, it cries. Within 24 hours, we'll see water droplets form at 90% RH, relative humidity, you'll see water droplets formed. And we have an actual sample of that today.
Right, so that's actually what these chambers are behind us. These are climatic chambers where we can simulate temperature and relative humidity to actually simulate that condition of in situ for that material being installed. Right? Mm-hmm. So then we start to see these water droplets, which could in turn cause corrosion. Mm-hmm. And this is exactly what this can look like.
Exactly right. So what happens, you ask, well, what's the process? You'll see water droplets form, but then it's a tug of war. You now have a hydrate material here absorbing water, the droplets being formed. If you allow it to evaporate, salt crystals form, but then the OSB, the wood material, actually starts to absorb that water. So the little layer here, right in contact, becomes saturated within 24 hours. So you're talking about a situation where one wants to be a sponge and one wants to be a sponge from the atmosphere. The wood wants to be a sponge from the magnesium oxide.
Right, so we're being very hygroscopic, right?
Indeed,
so
yes.
Is this a good test for users or specifiers to use to understand if their material is good quality or not?
Absolutely it is. A halogenation test is what we call it. And technically it's dehalogenation, because what's happening is that salt, as it's being formed, or as that liquid salt's being dissolved into the liquid, then that evaporates, leaving behind the salt. So technically, you're dehalogenating the material.
Right, so that halogenation, dehalogenation, we actually talk about in our white paper.
That's right, we do.
So, if you haven't seen that, it's gonna be in the show notes. Feel free to read that, come back, because it's really important with this material, magnesium oxide, to understand halogenation. And halogenation is kind of a term that we really don't use here in North America and the United States regarding testing of materials. It actually came from overseas in Asia, from China. And that dehalogenation test, which is actually using this climatic chamber, is actually within that Chinese standard of GBT 33544, which actually has a halogenation test of 90 degrees and 90% humidity for 72 hours.
You know what's I like simple tests.
Yeah.
And I think you can convey a lot of information in a layman's point of view. That's a very simple test. It's nothing more than putting the material into the chamber, 90 degrees, 90% RH, let it go for 3 days.
So you're letting it go for 3 days. If you start to see water droplets on that material within that 3-day time frame, is that a cause for concern?
Yes, it is.
Absolutely. So is that what we're seeing as free chlorides, for example?
Free chlorides and free magnesium chloride in this case. It's not the chloride per se, but it's the salt, free salt that is not hydrated.
Right. So is a halogenation or deliquescence test, is that a sign of overall free chlorides within the material?
Yes, to some degree it is. Right. It's a little misnomer out there in the magnesium oxide world. The assumption is if you got low free chlorides, you're never going to have weeping. And that could be true. But if you have higher than, let's say, 5% free chlorides, are you immune from getting it? No, you're not. You could go higher than 5% and still not have crying, weeping, or deliquescence. It really comes down to the free magnesium chloride, not just the free chloride per se.
Right, so this is similar to efflorescence in the masonry industry, where we're seeing that salt show itself on the face after the water vapor has, evaporated or things of that nature.
Exactly right.
Right, so essentially you're evaporating it within the chamber, or you're adding the humidity within the chamber of the water, and it's evaporating, leaving that salt.
That's right.
Right. Yeah. So to kind of wrap this up a little bit, when we see this halogenation and deliquescence within MgO, is that a sign of a bad material? And do you have to have a full chamber to run that test?
You need some means to get up to 90%. You can do that with
salt. Are there ways to do that?
Yeah, I used to do it in my lab in Minnesota all the time. I just put a salt concentration till I knew that I was going to achieve an 85, 90, 95% RH. Not as accurate as that machine back there, but I can dial in pretty good. It's a simple test. You can do it in any lab or even in a garage.
Right, and this test of 90%, 90 degrees Fahrenheit and 90% RH is actually now found its way in AC 386, which is the acceptance criteria for magnesium oxide within the corrosion appendix A, which is exposure category 1, which we believe is one of the most stringent tests and really the first barrier for entry for using of magnesium oxide. And that's really why we wanted to bring this to light today, because it's not so much that it's a magnesium oxide joined to an OSB material, it's really the chemical nature of that magnesium oxide that's cause for concern.
Yeah, let me expand on that. Is that you asked, what does that mean to the material? If you have the free chlorides and you have that deliquescence happening, does it mean that the formulation's off? It absolutely means that the formulation's off. A good magnesium oxide, whether it's being hybridized to a material like wood or whether it's a freestanding magnesium oxide panel, it will not deliquesce. It will not weep. So yes, I'm calling it out. This is not a well-formulated magnesium oxide panel.
Right, so really to wrap that up, the cause for concern here is if you're using a material with magnesium oxide coating, in this case LP flame block, you should be cautious about corrosion and long-term use. And that's really what we're trying to say.
That's
because of
a good
this
way.
simple weatherization, high, climatic chamber test that you could run at home or in a lab such as what we have here today.
Yeah, well said.
Yeah, absolutely. Thanks for joining us today on Built Environments. This was a quick conversation, but there's lots more that we can discuss. If you have further questions, be sure to leave them in the comments below or shoot us an email from our website.
And don't forget to check out the white paper on our website and LinkedIn. We'll be posting more on this topic and a lot more.